We are recording. Okay, so let me hand over the floor to group 5 and let them share with us their design.
All right. Hi, we're group 5. So we're here today to show you our design for a small scale heliostat named the Illumigator. Our team comprised of the 8 engineers listed below. So Bryce Bem, Christopher Bohr, Daniel DiCario, Alfredo Delgado, Ethan Hadorf, Jacob McKishney, Kieran Mithel, and myself, Spencer Steinmetz. All right, so today we're going to go through a product overview, our core value proposition. We're going to analyze the support structure, anchoring device, our mirror array module, our control system, some of the hardware that we have. We're going to also present a cost table summary. All right, so right here we're showing our 5 physical subsystems. So that's going to be the mirror array, our support structure, our anchoring device, our computer mount and associated hardware, and the module. Let's see. It's also notable that this uses a wooden construction, 2-axis pulley system. There's a Ujoint used to position, also a wooden stake anchor and mounting clamps. All right, so here we utilize a timing belt for the pulleys to avoid slippage issues, utilizing a 3D printed timing pulley so that could properly interface with the belt. Additionally, a 6-volt, 6 RPM reversible DC motor was used to drive this. All right, so for our core value proposition, it was desired that we design a heliostat to utilize solar energy. To this end, we created the Illumigator. So our solution stands apart from competitors with its high manufacturability and ease of construction. We plan to monetize this by selling the electricity produced from our design.
So the image depicted on this slide is our customer needs map. Maps every customer need to their respective subsystems, and all of the needs will be addressed for each subsystem during our presentation.
Our first 2 subsystems are made of our primary material for our entire design, pine wood. It is pressure treated, which prevents termites and rot, as well as painted white in order to improve its longevity and further protect the structure from other environmental factors such as corrosion. Inside the support structure are 2 motors, 2 pulleys, a universal joint, brushes, our control system, and timing belts. These timing belt pulleys will allow for module actuation, and to reduce in cost, we went with the route of 3D printing the universal joint and the pulleys. The pulley system is done in a way that will enable it to move the heliostat in both the azimuth and elevation directions, giving us 2 axes of motion. Brushes are used to prevent environmental contamination of the motor and the pulley. And the anchor subsystem is a simple stake made from the same pressure-treated pine wood digging into the ground at a length of 2 feet. We went with simple but effective choices in these designs.
As mentioned earlier, our support structure and anchor system feature a predominantly wood-based construction. Our reason for choosing wood was based on its low cost and density, its modular features, relatively long lifespan, and an Ashby plot analysis. The Ashby plot analysis depicted here uses a strength to density value index to select a handful of candidate materials. And out of all these materials, wood received the highest value index score, indicating that if we want to optimize our design to be both lightweight whilst also meeting the minimum strength requirements, then wood would be our best choice for the material. And then an additional Ashby plot analysis was performed using the strength to relative cost per unit volume value index. In a similar fashion, a handful of materials were selected, and wood just happened to have the highest value index score, telling us that if we want to optimize our design to be both cost efficient and meet the minimum operating requirements for strength, we should select wood for our support structure and anchor system.
So this is a closer look at our U-joint. So you can see in the exploded view in the right how it's assembled. So we have the 2 base pieces and the centerpiece, and then 2 collars that are all 3D printed. And then we have 2 clevis pins for rotation and 2 cotter pins for locking them in place, which are both purchased off the shelf. And so we wanted to make sure that it was structurally sound to support the weight of the module. So we did a very simple analysis of the stresses acting on the U-joint. So we had a downward force from the weight of the module, and then 2 moments on either axes from the tension in the pulleys, which we had calculated already. And so that resulted in 2 normal stresses, one from the downward force and one from the moments, as well as a shear stress due to torsion. We used those to find 2 principal stresses, sigma A and sigma B, represented here. And then because the biggest stresses were acting on the seal pins, we compared the principal stresses that we found to the tensile strength of that steel, and we put it into 2 different brittle failure criteria because that material is considered to be brittle, and we ended up finding a lowest factor of safety of 2.58, which does exceed the customer need of having a factor of safety of at least 2.
To ensure that our design met the minimum factor of safety requirement for our support structure, we decided to analyze the applied torque acting on our motor system when the module is perpendicular to the wind force and the full weight of the module is acting on our support structure. This was accomplished by determining both the volume and the density of the materials making up our module, which is wooden beams and silica glass. By multiplying the volume times the density, we obtained a total mass for our module and mirror assembly. This was then converted to a force. And then after that, we determined a concentrated wind force based on the module cross-sectional area, a drag coefficient, and a distributed force from 35-mile-per-hour winds. Both of these forces were then combined to obtain a value of 308 newtons for the operating force on our timing belt and motor. This force was then multiplied by the radius of our pulley to obtain a torque of 6.87 Newton meters, and then compared to the stall torque listed by the manufacturer of our DC worm gear motor. From that, it yielded a factor of safety of 6.43, which exceeds the minimum requirement of 2 stated by our customer, indicating that our support structure does indeed meet that requirements.
So for the support structure, we wanted to determine the lifetime of these motors. The top value for this ratio down here represents the arc length of travel for the heliostat, while the bottom represents the circumference of the timing belt pulley. These ratios are multiplied by 2 to account for the heliostat returning to its original position at the end of each day. And this roughly equates to 6 and 7 cycles per day respectively. And from this, we are able to find the number of cycles over the course of 20 years for both motors. And on the next slide, we were able to create an SN curve for the falling motor shaft, and we assumed it was steel for the material. These following formulas calculate the completely reverse stress, the variables A and B, the endurance strength SE, the various Mirren factors, and then the shear stress to obtain the number of cycles to failure. This yields 119,560 cycles, which is more than double the number of cycles the motors will go through over 20 years. Because of this, we can be certain that the motors are not at risk of undergoing fatigue failure.
So one of the big concerns we had with using wood was that wood is known to be a pretty good insulator, and it's going to be housing components that are generating power, and we didn't want the power generating components to overheat. So we did a simplified heat transfer analysis of the support structure. You can see in this figure below, we did a steady state analysis considering conduction and convection. Because we opted to paint our support structure specifically with white paint, we were able to neglect the radiation effects here because white paint tends to have reflectivities really close to 1. So we found the power generated by all the components together, and this is a maximum value, so a worst case scenario of about 58.9 watts. And so accounting for, again, the worst case scenario with the highest temperature ever recorded in Las Vegas and then a high wind speed in Las Vegas, we were able to find the surface temperature of the wood, and we used that in an iterative process to determine the temperature of the components. And we ended up with a temperature of 37.45 degrees Celsius. So even though this is a very simplified analysis, it shows that we have a lot of leeway because the operating temperatures of the motor and the hardware have upper limits of around 70 to 80 degrees Celsius or even higher. And the PETG, which was used to construct the pulley, which is 3D printed, that has a glass transition temperature close to 80 degrees Celsius. So we could determine that pretty much everything was thermally safe.
All right, so here's the anchoring analysis. So for this, we approximated the dirt as a fluid that provided a distributed force that would increase with following depth. A momentum balance was then done on that, in which we were able to calculate a maximum perpendicular force that our anchoring could resist. And that was found to be approximately 170 newtons.
The support structure subsystem satisfied 5 of the customer needs. Each module had to be capable of tracking the sun throughout the day. And in our design, the pulleys allow us to move the heliostat in these 2 axes of motion, the azimuth and elevation directions. The customer wanted modules that were able to redirect sunlight to the receiver target, mounted on a tower up to 100 meters. And in our design, the pulleys will allow us to tilt the mirror in a manner to reach this number. The support structure uses parts that were equal in price or less expensive than the closest OTS part that was available. And in our system, our OTS parts are the 2 motors, timing belt, and screws. The factor of safety for all mechanical features in the support structure exceeded a value of 2. As shown earlier, the motor's factor of safety was 6.43 and the Ujoint was 2.58. Operational lifetimes had to exceed 20 years, and the wood we've selected has a lifetime of 35 years, which is well past this limit. In our anchor subsystem, the need for the system to operate under Las Vegas conditions was desired. And in our design, it withstands wind speeds above 35 miles per hour. And the lowest factor of safety regarding withstanding wind speed was found to be 2.23, which demonstrates it will meet the Las Vegas conditions.
Our mirror array features 4 OTS mirrors per heliostat. We were able to ensure that there is minimum tracking error by implementing an encoder in our design. And we also ensured that our heliostat could withstand a lift force of 35.756 pounds for maximum wind speeds at 35 miles per hour. Overall, our mirror array construction is pretty simple, consisting of 4 mirrors put together in our module, where it will be clamped down with wooden clamps.
So one important statistic when designing a concentrated solar plant is knowing the maximum receiver temperature, and then you could use that to find the efficiency of the entire plant. So to find this temperature, we minimize the absorption efficiency, set it equal to 0, because that would be when the receiver temperature would be at a maximum. And so we found that receiver temperature by using a solar concentration ratio of 1,000 per customer needs, as well as a useful power output after losses of 1 megawatt, also according to customer needs. And then we looked at irradiation on a tilted surface based on solar data from NREL's solar database. And then we plotted this graph of the receiver temperature throughout the day on the winter solstice, which is the day in the year with the least solar radiation. And we found a maximum temperature for the receiver of 2022 degrees Kelvin. And this was pretty much on par with a lot of concentrated solar plants. And we used that the way this was relevant to our design was that we used that to find an efficiency with the total area of the reflective surface across the field, which we will calculate in another analysis. But that gave us an efficiency of around 37% for our heliostat field.
Since our customer requires us to design a heliostat that can operate in ambient conditions in Las Vegas, Nevada, and also withstand cleaning forces, it was important to note the effects of wind shear and cleaning on our module and mirror array systems. To do this, both systems were approximated as a cantilever beam, with the fixed end behaving as the middle of our module. The 2 forces shown were calculated by determining the distributed loading of the wind force multiplied by half of the area. As you can see here, a value of 75.1 newtons was obtained and applied to the middle of the beam. The 6.2 Newton force at the tip of the beam was calculated by taking the cross-sectional area of a conventional hose nozzle and multiplying that by a minimum pressure washing pressure of 500 psi or 3.4 megapascals. Once these two forces were obtained, they were substituted into a simplified form of the bending moment stress equation for cantilever beams. After calculating these two stresses, a combined stress due to bending of 0.8656 megapascals was obtained. When compared to the ultimate stress perpendicular to the grain of wood, a factor of safety of 2.67 is obtained for the wooden beams used in the module. And compared to the ultimate tensile strength of silica glass, the stress is considerably smaller than the 1000 megapascals it's rated for. So we can ensure that both our mirror array and module systems are optimized to survive operating conditions in Las Vegas, assuming operating conditions is just withstanding wind shear and cleaning. Next, we decided to consider the effects of thermal expansion to decide if our design needed any kind of spacers or standoffs implemented, since our glass mirror array is flush against our wooden clamps. In order to do this, we use two thermal coefficients of expansion and a change in temperature of 13 degrees Celsius to reflect the average increase in temperature on hot summer days in Las Vegas. Taking these two values and multiplying them by the length of our parts, we obtained a strain of both 7.15 micrometers and 7.53 micrometers. And then when multiplied by the Young's modulus for both materials, we see that the resulting stresses are considerably less than the ultimate stresses noted in the previous analysis. From this, we can conclude that the forces induced by thermal expansion will not cause any form of plastic deformation, yielding, or fracture to our glass, indicating that our design is fine as is and will function accordingly. Our customer needs met by our mirror array are that the area is 1 meter squared, since each mirror array is 0.25 meters squared. Each module is composed of 4 to 16 heliostats. Our module can contain 4 mirror arrays as demonstrated. The reflective surface is washable. It can withstand forces from pressure washing and cleaning. A focal thermal input power of 1 megawatt after losses is ensured after the heat transfer analysis and temperature of the receiver analysis conducted, in addition to a solar concentration ratio greater than 1,000 suns. Our design also accounts for light dispersion by having a flat mirror array design and a flat module design.
The module subsystem consists of 3 pine 2x4s that are secured together using corner brackets and wood screws. There are 4 wooden clamps attached to the end of each beam to secure the mirror array. Since the module is made entirely of wood, it has a low weight of 6.3 pounds. Using the pulley system, the module is also capable of dual axis solar tracking.
So one of the key customer needs that was addressed by this subsystem is that there wouldn't be shading between modules. And so we took these steps to make sure that wouldn't happen. So first we determined the reflective area, that parameter that was used earlier. And we did this by first finding the area of the receiver, which would be the power input per the customer needs, divided by the solar flux, which we obtained from the solar database. And we found that the area, or using a concentration ratio of 1,000, which we designed for, we found that the total reflective area of the heliostats across the field was 2,859 meters squared. And so designing for the maximum 1 meter squared area per unit, we found that we would have 2,859 heliostats across the field. So to determine shading within the unit, we saw that 0.018 meters squared were shaded by the clamps used to hold the mirror array steady. And so that slightly increased our number to 2,913 heliostats. And to determine if there was shading between the heliostat units, we first looked at the field size. We assumed that it was 100 meters in radius. And so we looked at half of the field, assuming that none of our heliostats would be facing north because we're in the northern hemisphere. And so we divided that field area by the number of heliostats and determined that we would have about 5.4 meters squared of space per unit. And so looking at the length of the shadow, we maximize this by taking the solar angle at sunrise, which is assumed to be 0, and then the height at the maximum tilt angle of our heliostat, which was 55 degrees. And so because it was maximized, the length of the shadow is the same length as the height of the heliostat, which is 1.14 meters, which is much less than the 5.4 meters squared between heliostats. So there is sufficient spacing and there shouldn't be any shading in our field, which addresses that customer need.
So another analysis was to determine the maximum possible lift force on the heliostat module that was generated by the wind. To do this, we use the equation P for wind pressure. This is an approximation used by civil engineers. And this wind pressure can be multiplied by the area of the module in order to acquire wind force. And then assuming an angle of 45 degrees, a top wind speed of 35 miles per hour, and a module area of 1 meter squared, we can get a vertical force of 33.756 pounds. And the heliostat's total weight is 38.65 pounds, which is greater than this lift force. So this is not a likely mode of failure for our design.
The module subsystem met 3 more of the customer needs. The total collection area of a single heliostat module needed to be less than or equal to 1 meter squared, and ours was exactly 1 meter squared. The heliostats within a module couldn't shade other heliostats in that unit. Our heliostats are not designed in a way that their installation will require shading of other modules as shown in the analysis slide earlier. The total module area relative to the reflecting area needed to be small, preferably under 20%. In our design, the module covers approximately 2% of the reflective surface, clearly meeting this need.
So our next subsystem is the control system. So you can see a little block diagram there. Basically, it's a closed loop system. It's a bang-bang controller with a deadband, which is a similar system to how something like a AC unit works. So basically, the central computer will be determining when each mirror has accounted for enough tracking error to want it to move again. Once the central computer decides that, it'll send a signal to each heliostat and say, hey, it's time to move. And then that will be used to actuate the motors, basically. So one of the interesting things is that it is closed loop. So we have an encoder on each heliostat. So there's 2 encoders per heliostat, 1 on each shaft of the pulley. And yeah, using that, we could find out that the maximum tracking error due to these encoders is 0.8 degrees. So, so yeah, just using the PPR of it and based on how many rotations we're going to be doing throughout a day, it's 0.8 degrees is the maximum, although it is not the average. The only other sources of tracking error that we found as a company were possible thermal expansion of the pulley and the timing belt, which could be accounted for programmatically at the central computer if it has like a thermal probe. And basically, you could just modify the numbers that it sends to each heliostat by a scale factor. And yeah, another possible source of tracking error that we saw as a company was just the central computer itself not having good solar data, which is something that was outside of the scope of what us as a mechanical engineering company are going to do. So yeah, basically maximum tracking error around 0.8 degrees. Yeah. So these are the needs that we met. So we minimize the tracking error using the encoder. We're not going to be building up tracking error over time or anything. We have a built-in dual axis solar tracking. You can see that in our pulley system, and basically the control system allows for that to happen. And again, feedback control. Therefore, we have a high operational lifetime because our heliostat actually knows where it is over time. It's not just going to accumulate error. And then here's our computer hardware that we use to cause all that to happen. So basically, if you remember, the wooden structure of the support structure is environmentally sealed. It's got those brushes to prevent sand from coming in. So this is an added layer onto that, adding like moisture protection as well. So we could put all of the computer components into what is essentially a racquetball holder. And since it's under no forces, there's no issue with us putting it on like just a wooden panel. So we do that. But basically, all the hardware is a breadboard that has an Internet of Things board attached to it. So that's like a similar board that you'd see put in like an LED shirt or something. Super low power consumption, and it is not very good at processing things. Although it can bring in a Wi-Fi signal, and our central computer is doing all the processing. So we get that in, and then we drive that through a motor driver that ups our ampage, so that we could control the motors. Not pictured in this, though part of the computer control system is the 24 PPR optical encoders, which are on the shafts of the motors. But yeah, that's our computer stuff. So here are the customer needs that we met with that. So we have computerized tracking by our central computer. All the calculations, again, done by the central computer. It just basically tells a little Wi-Fi board what to do. And that tells the whole system what to do. And we also utilize OTS parts everywhere. The IoT boards are super duper cheap because they're not meant for like heavy processing, like something like an Arduino or a Raspberry Pi. And aside from that, it's all OTS.
So the total cost of the mirror array subsystem is $21.48, which counts for the cost of 4 silica glass and aluminum mirrors. Total cost of the computer mount and hardware is $16.81, which is all of the OTS parts shown. The anchoring and module subsystems have low costs of $5.13 and $17.42 because they only consist of wood, paint, and fasteners. And the support structure had the highest cost of $65.62 because it houses all of our working components and uses the largest quantity of wood. The total cost of raw materials is $126.46, which includes all OTS and manufacturable parts. Since our design is simple and primarily wood, it's easy to shape and manufacture with a bandsaw, creating a low manufacturing cost of $8.42. Based on the Boothroyd and Dewhurst assembly time charts, our design had a total assembly time of approximately 31 minutes, which creates the low assembly cost of $12.90. And the energy consumption during manufacturing is only 2 cents, which is very low cost for producing something such as a heliostat. And accounting for all these costs creates a total of $147.80 per 1 meter squared.
Sorry. So another cost that we thought might be useful for the customer to know would be that of the manufacturing facility. And we got these rates off of Nevada Energy, which is a local utilities company in Las Vegas and all of Southern Nevada. So this energy cost consists of the customer charge, which is the fixed monthly charge from the energy company, the fuel charge, which is the cost for them to generate the electricity, the non-fuel charge, which is for them to deliver, and then the demand charge, which we based off of our demand of 1 megawatt. And so that ended up in the cost of $13.22 per month, which we thought would be pretty useful for the customer to know.
Here we have a chart depicting the range of technological readiness for our product. Level 1 represents the lowest level, consisting of initial observations and researching of basic principles. And then it goes all the way up to level 9 with real world operations and applications. For our heliostat, we believe we're between levels 1 and 3. We've performed multiple analyses for our design subsystems and have conceptually proven our idea.
So here's our last slide. I'm just going to talk about the design overall and the benefits that we have that are outside of all of the low costs and general needs that we have already met within the rest of this report. So our designs excels at a lot of things like not at first glance you'd see. So for instance, our design is built to last over 20 years, of course. But we are also one of the most modular designs out there out of the teams that we've seen. If any components were to break on this design, They could be very, very easily replaced. Everything is basically secured via a fastener. So if you ever need to replace a component, you just have to take the fastener out. And they're also wood components. So if you ever needed to fix something, you could basically fix it on the slot. You just cut out another piece of wood, jam it right back on there. It's good. Put the fastener back in. Awesome. So yeah, our whole design, there's no permanent connections, no bondings that can't be removed, and no component is intrinsically connected to another component and can't be separated if a repair were to need to happen. Another beautiful thing about our design is just the simplicity of it all. Simple wood cuts. We have very, very loose tolerances on everything. And yeah, so you would never have to send this to like a machine shop or anything. And this could be assembled with by people with very low like technical competence. All that's required for a majority of the structural design is a saw and a hand drill, or a bandsaw or a hammer if you want to change out the screws for nails, which is a possibility. It's so simple. It could be built by like non-industry sources as well, which is another factor to consider when picking our design in our company. We can get people involved in actual solar energy production who have no experience in engineering or manufacturing in general. So that sounds all good for solar energy, get the community involved, but why would you as a company care about how we do our manufacturing at our company? Well, because of our like custom way, or because of the way that our design is made, and how we conduct our manufacturing, additional cost savings could be conveyed onto you, the customer, which are not fully accounted for in our current overall costs. This may come in the form of free labor, reduced labor, and possibly free materials or reduced price materials. And lastly, the fact that we are the only company to figure out that the entire design can be made out of wood also helps in ways not conveyed in many of the costs you are likely getting from the other companies. Wood shops and lumber production is much more competitive than something like aluminum production. And it's also much more widespread than something like aluminum production that would cut down on shipping costs. And we could get additional cost reductions from that via playing manufacturers or raw material suppliers off each other, which is not something you could do with something like aluminum or steel. Shipping costs are also reduced, as well as disassembling the fields will be much easier with a wooden design, with our anchoring design that could just be basically really, really pulled out of the ground. So if you ever needed to disassemble a field for any reason, that could also be much easier with our design. Also, just in general, our design is much better for the environment in general. Renewable resources, which is something as a solar energy producer, we kind of pride ourselves on, using renewable resources rather than something out of the ground like a metal, especially when like aluminum production and steel production takes up so much of the energy production, energy grid of the world. We decided that something like wood would be a reduction in that. But yeah, that's our company, that's our benefits, and that's the basic summary of everything we've got. And we are now open for questions.
Okay, I got a list of them. You ready?
I'm ready.
Okay, it seems like there isn't any provisions in your design for lightning protection. They do get thunderstorms out in Las Vegas, and if you take a lightning hit, it seems like that your wooden structure is going to become a heating element and catch on fire. Is there any type of grounding, earth ground to protect against lightning hits?
On the field itself, we would be installing like lightning rods or something similar to that to try to prevent that opportunity. But if an individual heliostat were to be hit with a lightning strike, we have enough spacing in between them where you would just break one heliostat.
Yeah.
So
Additionally, the receiver itself, which would be at the center of this, would be easily the highest point. Like these are going to be really low to the ground. So the likelihood of them actually striking a heliostat would be very unlikely in my mind, as opposed to the main tower. And that wasn't part of our design, I guess, requirements.
Yep. Okay. The other thing I noticed is in your design, I didn't see any travel stops or travel limitations on the articulation of the mirrors. And it appears that you're using the actual motor as a brake. So normally in these articulating designs, there's a mechanical stop that would prevent or actually define the limit of travel. And this is kind of important for a couple reasons. Number one, if one of your belts were to fail, the amount of movement that the mirror would actually be exposed to is somewhat limited. And then the other thing is, I didn't hear you talk about it, but it appears that you're using the motor itself as a brake. In other words, once you turn the motor off, there's some type of a brake inside the motor that actually holds the mirrors in a position. And if that's true, then the life of the motor would be a function of cycle, how many times you actually move. And I'm wondering if you took that in consideration in your calculus when you defined your motor life.
So we believe that most of the force of the motor just sitting there. So for instance, if the mirror is angled like this, that's going to be held. A lot of that tension and force is going to be held within the pulley wire basically. And the only force that the timing belt, and the force that's on the actual motor itself is just going to be that same upwards force that's caused by that tension. That's the same force that's basically keeping the timing belt on the pulley. Does that answer your question?
Well, what I was concerned about is what's actually in a park position. Where is the force being applied to prevent the mirror from moving? Is it the motor? Does the motor become the brake, or is there some other mechanism that when the mirror is parked, when it's in a position you want it to be in, and if wind is acting upon it, what's preventing the actual movement of the mirror? And I'm assuming it's a brake inside of the motor, but I didn't see that.
So part of that, I think, is accounted for in the fact that we're using closed loop feedback. So any adjustments in the actual position versus the desired position is covered by the encoder. And so we can readjust the position accordingly.
So from a reliability perspective, that's probably be a bad idea using constant adjustments via encoder feedback based on potential movement from wind loads. I just think you need to take a look at how you are going to park the mirrors and what concept are you going to use. It seemed to be missing from your presentation, and that's really important because that's going to determine the failure rate of the motor. If you're going to rely on that motor, the internal brake on that, then you got to take that in consideration in your mean time between failure calculations. So there's a couple other things that I wanted to talk about, and one of them is calibration. You would want to have your design so that you could synchronize all of your mirrors in your array. And normally what's done is in the gearing, in the timing belt gear, there's usually a hole drilled through there that you could insert a pin. So when you install these heliostats, and every one of them gets installed and there's a pin inserted, and the encoder reads that position, and that becomes the reference position for all the mirrors. And then each mirror then could be adjusted from that reference position, because that way there you could synchronize all of your mirrors in your array, because they now have a known fixed reference point that was used as part of calibration when you did your initial installation. So you might want to take that in consideration. The other thing is, I noticed that your stepper motor or your drive motor that you're using appears to be secured in place by a clamp. And it seems like as you apply torque to the output of the motor, it's going to want to put a twisting moment on that clamp. And I'm just wondering if you did any work to see if the single clamp arrangement that you have is going to be adequate enough. Now, maybe that clamp is welded to the motor frame that provides additional support, but if it's just using a friction type of a clamping force to prevent rotation, you might want to look at that. The other thing I noticed is maintenance access. There will likely have to be a maintainer getting access to the internal electronics to either make repairs or recalibrate and so forth. I didn't see anything where there was a panel that you could take off to get the maintainer access.
Yeah, it's just you could take off any of the fasteners. The whole assembly is put together with fasteners. So although there's no like easy to open panel, I guess you just have to take off. I think it'd be a total of 4 fasteners to get to the computer hardware.
Okay.
And then that just has a lid on it, which you can screw off because it's like a rack
Okay.
ball.
They just got to make sure they take the right panel off, the right side off, because some of those sides have motors mounted to it and so forth.
Yeah, they'd be. Yeah.
So the other thing I was concerned about is the serpentine belt that you have, the timing belt. Over time, and especially temperature, those might incur slack. Normally what's done is there's some type of an idler pulley on a spring that maintains constant tension over the life cycle. And I didn't see anything like an idler pulley to maintain constant tension on that belt. And it is a relatively long belt, so you are going to get some slack develop over time. And you might want to take a look at that as well.
Yeah, that's something we considered originally. We tried calculating the minimum length of the pulley.
Yeah.
Further measures will be taken to determine like what will happen to the slack of the pulley after time over operation.
Okay. On your electrical control system, I didn't see any overcurrent or fuse protection. If something were to fail, what is the protection so that it doesn't become a heating element and catch your whole heliostat on fire? So normally there's some type of a fuse even on the power input going into the heliostat. It should have some type of overcurrent protection device. And then the last thing that I had is, did you do any thermal analysis on your electronics, being that these things are going to be in a confined box in the Las Vegas desert, and the ambient temperature and the solar load is going to get relatively high inside of that wooden structure? And could your electronics tolerate those temperatures?
Yeah, so based on the thermal analysis we did for the support structure, so because all of our hardware is inside the support structure, it shouldn't have to worry about radiation or conduction. And so the main cause of concern is the container trapping the heat inside and causing convective heat transfer. But it shouldn't be a problem based on the maximum conditions we use. We found our maximum temperature of the air that would happen inside the support structure, and that wasn't high enough to bring the components past their operating temperature. And if the components, they generate very little power, but if they were to generate that the heat would get trapped inside that container, it would pretty much just be as simple as cutting holes for ventilation, or if necessary, providing forced cooling, but that shouldn't be necessary.
All right, and then the other thing I think you answered, and you kind of touched on this, is anytime you have a perforation or any type of access externally, you got to take in consideration insect or rodent infestation. And insects tend to contaminate electronics. They end up bridging gaps on pins and so forth. And rodents like eating wires. And I think you mentioned that your design was hermetically sealed. So I don't know if you do have any cooling perforations or ports or anything, but in the desert, you got to expect insect and rodent infestation as a potential failure.
Yeah, so the wood itself is not only is it sealed with the paint, it also has sealant on it, and it's pressure treated, all of which provide some form of protection against insects like termites and stuff. But for more general insects, we also have like a brush system on the outside of the support structure, which could prevent larger rodents from getting in. And for the computer mounting hardware, all of the connections that we'd be scared about, which would be like soldered connections and stuff like that, those are all those would all be within a structure that no insect can get into. And any sort of connections that we'd have outside of that would be covered in some sort of protection against that.
Okay, just two more questions. During maintenance, considering the maintainer, it's important that you could secure the mirrors. In other words, lock them in place. If a maintainer had to replace a motor or a serpentine belt, you don't want that thing flailing around and potentially hitting the maintainer in the head or getting their fingers caught in some articulating surface. So you might want to consider having a mechanism to lock to lock the whole mirror in a certain position, whether that's a through bolt or some type of a lock mechanism in order to protect the maintainer. And the last question is, did you guys do a finite element analysis to determine where your most vulnerable yield point is in terms of wind loads?
I believe we were in the process of conducting a finite element analysis on our Ujoint possibly, but we haven't explored that fully yet.
Okay.
Guys, I know we're running short on time here, and I just wanted to pop in with a question about your error, if your degrees of error, if that's okay.
Sure, go for it.
Hey, this is Kim, by the way, and I'm one of the grad students in the NCR lab on campus. I have a question: how you calculated the 0.8 degrees of error in your system?
Sure. So we have basically the optical encoder we're using is 24 ppr. So depending on how many rotations we have, we can convert that into an error of, I guess the lights. Convert that into the error of like the vector coming out of the perpendicular face of the mirror. So that's what that 0.8 degrees is. Basically, we know that we're spinning 66 times in a day. So we know that 55 degrees of motion that we have in that axis is within that. So just doing some basic division, you can find out using the 24 ppr that we update our motor. I think it was 66 times a day of its actual position. And if you divide that by the 55 degrees, you can get the 0.8 degrees of encoder error.
Okay, so to get the full array that you're looking to attain, you're counting on 66 rotations of your motor?
No, it ends up being, I think, 6.7 rotations of our motor. I'm not sure, the calculation's in a different slide, but using that and knowing that we have 24 ppr, so the encoder knows where it is 24 times in one cycle, and we have 6.7 cycles, it ends up being Yeah, it comes up.
Okay, so if you have a 24 PPR encoder, that means that every 15 degrees of encoder rotation, there's a click, right?
Mhm.
So if you're rotating 6.7 times, that means you have 2 degrees roughly. I'm doing this in my head, but 2 degrees between a pulse on your encoder. And that's across 2 different encoders. So it seems to me
Yeah.
that your error is higher than you're reporting. I
Okay.
mean, not intentionally, I'm just saying, check your calculations, you know?
Yeah. Okay. I appreciate it.
Yeah, because those really low cost, low grade encoders, you know, you get what you pay for, right? So I would also check on the accuracy of those encoders as well. So most likely your error is going to be a lot higher than you think. Also, can you go back to your shading analysis slide? I don't want to take up too much time, but this is one thing I just wanted to point out real quick.
Yeah, I can go back to it.
Thanks. Off the top of your head, can one of you tell me what the tangent of 0 is?
U1.
0.
Uh-huh.
0.
So what's the problem?
Yeah.
Oh, that would be the wrong maximum.
All right, so you got to be on the lookout for these kind of things when you're making a presentation. You know, dividing by 0 is a big no-no, right?
You could say it's an infinitely bad idea.
It is. So anyways, I know you guys have gotten a lot of feedback. That's all I'm going to say at this point. But yeah, just keep an eye on those things. A couple of the other issues I had, I think were already brought up. So good job. And I'll open the floor back up to whoever else wants to give some input.
Thank you.
Well, and so thanks, Kim. We're actually quite a bit over even the end of class, and today's still a regular class day. So I do want to bring the questions to a close there, because these guys might have a class in 10 minutes, and I want to make sure they don't miss that one. So can wrap it up there, but want to thank you guys for sharing your design with us and for all your hard work over the semester, and especially for not being afraid to embrace wood as your primary building material, and doing some of the analysis required to convince yourselves that it could actually be viable. So we appreciate you guys doing that. I think with that, we'll wrap it up. The next presentation today is at 2:00, so we've got a really big break, because again, this is a regular class day, not a reading day. So for the panelists, we'll see you again at 2 p.m. And with that, we'll call it a session. Thank you.
Thanks for coming by, everyone.
All right. Thank you.
Thanks, everyone.